In this video, we're going to compute the directional derivative of the function f of xy equals to x squared minus xy at a point P 2, 1 in the direction of the vector 1, 2. What we're going to see is that if we have the point and we move P plus certain amount V, this is 2, 1 plus s times 1, 2, which is equals to 2 plus s, 1 plus 2s. So we get a function g that depends on s equals to f of 2 plus s, 1 plus 2s. It turns out that the directional derivative of p f at the point P in the given direction is precisely the derivative of this new function when s equals 0, because for x equals 0 we have the point P. Similarly, the second directional derivative will be equals to the second derivative of the new function g at 0. Let's look at all this with GeoGebra. With GeoGebra, a directional derivative. Here is our function. You can see the function here, and let's look at the point. Our point is the 2, 1, and we have to put the third coordinate, which is the value of the function. So the point lies on the graph of the function. What we are going to do is take a series of points here, this point here, in the plane, and we're going to look at the image. So we create a new function, which is this function here. This function corresponds to a graph on the surface of our function. When the point moves, here we have, as the point moves on the graph going towards P, this is equivalent to ask the point to move here on our parabola and P corresponds to time 0. So these 2 points are one here in the graph of the function, and here what happens if we restrict ourselves to that set of points. So let's stop this for a second, and we'll see the directional derivative is nothing but here is when 0, the point P at 0. And we want to study, as I say, what happens as we approach P on the graph. But if we look at it as a one-dimensional function, one variable function, is the parabola here. Let's see. First, let's compute the partial derivative with respect to x. Is this one here. And then with respect to y, this one here, these two here. And let's construct M1, as you can see on the left. M1 is the gradient. V is our vector, and the directional derivative will be the product of the vector M1 gradient times the direction 1, 2, which will put transpose. We get minus 1 here. But if we look at the derivative of g as 0, it's also minus 1. Second derivative, here's the second derivative of f with respect to x twice. This is the second derivative with respect to y twice. And this is the derivative of a with respect to y. But a here is the first derivative with respect to x. So this here is f with respect to x, and then with respect to y is the cross derivative. Here you have the Hessian at a point. You want to compute the second derivative, you have to multiply the vector v times the Hessian times the transpose of the vector, and you get minus 2. But you compute the second derivative of our g function is also minus 2. And that's the meaning of the directional derivative. What happens when the point moves in a certain direction from a fixed point P. On the right here you have the three-dimensional picture, here you have the two-dimensional picture.